Hello wonderful person, this is Anton, and in this video we're going to be talking about yet another mysterious star in the Andromeda galaxy that seems to be exploding way too much. So the Andromeda galaxy is relatively far from us. It's about 2.5 million light years away from the Milky Way. As a matter of fact, this is the Andromeda, and if I were to try to point at where the Milky Way is, it's sort of right there, and it's actually barely visible. It's kind of far away. But even though it's so far away from us, we can still see quite a lot of things happening here, specifically when it comes to large explosions. And so very recently, only a few weeks ago from when I'm making this video, a new paper was published that actually describes a very unusual event happening around the star known as M31N 2008-12A. The event that I'm talking about is known as NOAA, and I'm going to explain to you in a second what this means. But what's so unusual about this particular event is that it seems to be happening every single year. And that's way more frequent than we usually see these happening. So anyway, first of all, what's a NOAA? Well, it's actually a little bit different, or very different from a supernova. What you're about to see is known as Type 1a supernova. This is when a star similar to what our sun is going to become, a white dwarf, reaches a mass known as Chandrasekhar limit. You can actually check out this concept in the video that should be popping up somewhere above my head. And once this limit is reached, the star basically explodes. Usually it kind of leaves very tiny fragment of itself in the middle, but sometimes it explodes completely. It creates a lot of energy and it's very powerful. And we normally use these supernova as a kind of a standard candle of measurement, basically because they always kind of explode with the same luminosity and the same strength. We can use this to measure distances in space once these supernovae are detected. And so that's how a lot of distances in space are measured. But these events are pretty rare. As a matter of fact, the last one in our own galaxy is like centuries ago. So it would be very unusual to find one nearby. On the other hand, there is another event known as NOVA, and that's actually a little bit different. So NOVA occurs also around the white dwarf, but for different reasons. For a NOVA to occur, a white dwarf, in this case it's actually Series B, the closest white dwarf to our solar system, it's only like 6 light years away from us, is orbiting its partner Sirius A. And as you can see, because it's orbiting so close to it, it starts eating up some of its mass because of the tidal effects. This object is super dense, it's very small, but they're about the same mass. And its partner star is relatively similar to our sun. It's much less dense. And this density basically causes the larger star to lose its mass and to slowly deposit it in a kind of a ring, accretion disk basically, around the white dwarf. So we might not see this here. I might actually kind of cheat a little bit and just add one manually. So there is that little accretion disk that is kind of difficult to see, but it's basically there. And eventually this disk grows larger and larger and larger and larger, and at some point reaches a critical mass, which is very similar to what happens in nuclear reactors if basically things go wrong. When a nuclear mass is reached, this whole thing here explodes in a very large nuclear explosion. Not a type of an explosion that supernova has, but basically very similar to an explosion that you'd expect from a nuclear bomb. And these explosions are extremely bright and are visible from really far away. Now, when a star goes nova, it normally repeats the process every decade or so. Sometimes every 20 years, sometimes every 10 years. It really depends on the star. But for this particular star that we discovered very recently, this process seems to happen every single year. It basically creates these explosions much more frequently, like 10 times more frequently than we expect. And this is where the mystery lies, because we're not sure why it's doing that. On top of that, because it explodes so often, it created this very large structure that's essentially 400 light years across. This is what the scientists refer to as a super remnant, and it's essentially just all of this material that was exploded in these large explosions for the past, I guess, hundreds of years, as soon as the star started going nova. And because it happens every year, more and more mass is added, and the structure keeps growing larger and larger. But there might be one explanation that the scientists think they have for this. The explanation is that it might be actually a kind of a natural progression of a white dwarf that has a partner, and what's happening here is that it's actually reaching its mass limit, known as Chandrasekhar limit, and as it's sort of reaching its limit, it starts throwing off more and more of these nova. It basically starts exploding a little bit more until it finally reaches the limit, and then when that happens, the entire star will basically explode and go type 1a supernova, and this will be extremely bright and quite visible from our planet Earth. Now, we don't think it's going to happen anytime soon though, and so unfortunately we're not going to be actually seeing this in the next few years, but the current estimate is that this might happen within the next 40,000 years. And if this is actually what's happening here, it means that we now have officially kind of understood the evolution of white dwarf binaries a little bit better. Because we've seen nova before, and we've seen type 1a supernova, but we didn't really know what happens in between. But this particular study seems to indicate that these nova that we're seeing will increase in frequency even more with time, and at some point it's very likely that the star will simply reach its limit and will essentially do this. This is a simulation that you can find in Universe Sandbox where you're shown how type 1a supernova occurs when the star reaches its Chandrasekhar limit. And so honestly, this is actually a pretty exciting discovery coming from Andromeda, specifically because when these supernova happen, it allows us to determine the actual distance much more accurately, and the effects of the supernova will actually produce some really interesting things as well. Now, at the same time though, we don't expect it to happen anytime soon, and if it does happen in 40,000 years, well, hopefully there are still astronomers around to actually observe it. And for all we know, maybe, just maybe, by then we might even find a way to actually go there. That would be pretty cool, right? Hello wonderful person, this is Anton, and today we're going to be talking about a new discovery of a very unusual star system where things are very, very different from what we expected. We're going to be talking about the system that you see right here on the screen, and I'm going to explain to you what actually was discovered there. Now, this system is known as HD 98800, and it's actually something we've known about for a while, but what we've discovered recently kind of changes things a little bit. Before I go into that, let me actually briefly talk about why it's unusual. So first of all, here is our Earth, and here is our solar system. If I were to actually look at the solar system sort of from this angle, and then to maybe move things sideways, you would see that a lot of things here are not entirely aligned. This is actually very common for various star systems, and many reasons and many sort of events can actually cause this, but pretty much every major planet and every major object in our solar system has some kind of an inclination. And normally it's something that happens in the beginning of the solar system when it's just created, and what we believe happens usually is when new material is added to the early solar system, when it's still in its infancy and when the protoplanetary disk is still basically being developed, things start kind of shifting around and the inclination may change. Now, for the longest time, scientists believe that sometimes so much mass can be added or so many things can happen that the protoplanetary disk can actually shift completely. It can actually be maybe as much as 45 degrees or maybe even be completely on the side. This is something we believed may actually exist out there, and in some sense it did make mathematical sense. So basically, instead of things orbiting this way, it would actually be orbiting sort of vertically. In our solar system, we actually do have some objects that do that. You can even find them here in Universe Sandbox. I think some of them are actually not present, but there's a few asteroids we've discovered that basically have a vertical orbit. And even planets like Earth and Jupiter, they also have a bit of an inclination. For Earth, it's very, very little. It's not even a degree, but for objects like, let's take a look at, I guess, Neptune that's near here, it's about 1.8 degrees. And the modern assumption that it's either something that happened a long time ago, or maybe it's also Planet 9 that's been causing a bit of a ruckus and changing the inclination of objects. So we don't really know what did this. But what we do know is that sometimes we discover new objects and new stars and new planets that don't really meet our expectations. And this is what's happening here with HD 98800. The study is actually this right here. You can find it in the description below. Circumbinary protoplanetary disk in polar configuration. It's by Dr. Kennedy and his team from University of Warwick. And in their study, they essentially focused on the so-called circumbinary planets, or in other words, let me just show you an example here. Imagine a binary star system, so here is one with 2 suns, that has planets orbiting around it. For the most part, if you watched one of the, I guess it's a pretty old video that I made a few years ago, one of the older videos I made about circumbinary planets, there's actually a calculation I did, and this is based on actual scientific findings, where it's super difficult for us to place an actual planet here for it to stay in a stable orbit. So here's Venus. Watch how it's actually not going to stay in an orbit. It's most likely going to just escape. So circumbinary planets are very difficult to maintain, unless they are vertical. If you were to place something vertically, so in other words, if I were to instead do something like this instead, basically making it a vertical object, in that case, it might survive a little bit longer. Okay, in this case, it didn't work because I didn't really do any mathematical calculations here, but a vertical alignment will have a much higher chance of surviving in circumbinary planets. And it just so happens that they just discovered one such star system where the alignment is basically vertical, and it's something that was confirmed with the pictures that were taken by the ALMA observatory. So interestingly, basically what this means is that this star system right here that actually does exist in Space Engine may have quite a lot of planetary objects that have not 1, not 2, not 3, but 4 stars, and the majority of those planets actually are circumbinary. Basically, they orbit 2 stars at the same time. So if I were to create this in a universe sandbox, it would look something like this. So we have our 2 suns here, and then we have 2 more stars that are orbiting around one another here. This pair of stars and this pair of stars are actually relatively far from one another. And this here will have a very interesting planetary disk around it that's vertical, kind of like this. And so assuming you're standing on a planet somewhere in this region, you're going to have, well, essentially 4 stars in your night skies, but also, okay, this is not really a planet, it's just a tiny object I've created. But also what you'll see is a very unusual view that might resemble something like this. This is actually one of the pictures that was created by the team behind this study. And if you were to stand on the planet, you would have these 2 stars, you would have the actual possible ring visible as well, and then you'll have 2 other stars in a distance. So this actually makes this particular system very interesting, because not only is it unusual in every major way, but it also might have, for those planets at least, very unusual seasons and very unusual and unpredictable seasonal changes, because here you have 4 stars, you have unusual inclination of those objects, and for every major planet here, it would basically be exposed to somewhat unpredictable amounts of radiation depending on the location in space. So don't expect these objects to have a typical winter and summer. Here, the actual changes in climate would be very difficult to describe. Now, living in these conditions might be actually very challenging, but also having habitable worlds in these particular locations would also be almost impossible, mostly because the temperature here could change from being very cold to very hot in no time. Now, it doesn't mean that we're not going to find a habitable planet here. It just means that finding a habitable planet in a circumbinary system is already hard, but finding one in a system with 4 stars is going to be even more challenging. Now, I'm actually excited to hear about what else we discover in this particular system, because it's already quite unusual. There's actually, you might not be able to tell, but there's 4 stars here. 2 are orbiting in this region on the left, and 2 are orbiting on the right. And they also orbit around one another. So if I accelerate time here, you'll see how they actually spin around one another in this very beautiful procession. So there's definitely a lot of gravitational disturbances here, and even the planets we might be able to discover in the future might actually not have a stable orbit. They might end up being completely shut out of the system or swallowed by one of the stars. But it's still interesting to see what actually happens here. I'm sure we're going to be able to discover something more unusual in the next few years, but for now this is probably the weirdest and most extreme version of a star system we've discovered so far. So not only does it have 4 stars, with 2 of those stars that actually do have a circumbinary protoplanetary ring around it, but we also seem to have this unusual formation with a practically vertical alignment that we were able to take a pretty good snapshot of, and we were able to see what's actually happening there. Now you might remember hearing about the Tabby star. It does have quite a lot of other names such as Boyajian star, or more specifically KIC 8462852. This is what it sort of looks like if you were to take a look at it from a telescope. And its mystery is related to its unusual dimming that was detected by the amateur scientists or citizen scientists, and later on thoroughly analyzed by several scientists, including of course the primary investigator whose name was later used to name the star, the Tabby star. So right now we don't really exactly know what's happening here. We know that this star does have a tendency to dim quite suddenly, and even in the last few hundred years or so, it seems to have decreased its total brightness by roughly around 20%. And although there were quite a lot of different explanations, including of course aliens, the best explanation to date was, well, actually kind of boring. It was literally this right here. Dust inside the star system. Although maybe it was actually dust from various cometary bodies, specifically comets with a relatively eccentric orbit. And this explanation was quite okay actually. It did explain quite a lot of things, such as for example why the star was dimming so unpredictably, and these eccentric orbits did explain some of the observations, but they did also fail to explain one major observation, the long-term dimming that was kind of unusual, specifically the dimming by roughly around 14% over several years. Now this would be something a little bit more dramatic. And so the new study that just came out a few days ago from when I'm making this video tackles this situation and tries to explain what's really happening to Tabby star according to these scientists. And in order to visualize all of this, we're going to be using Universe Sandbox 2, and here I just need 3 objects. I need some kind of a star, in this case that's the Tabby star. We also need some sort of a planet, and this planet needs to have a moon, very similar to moons like Ganymede and Callisto, containing both ices and quite a lot of rock. Let's choose Ganymede for this because it's the largest moon that we have and it does have the necessary materials. Now, as soon as I place it here, you'll notice that first of all it starts to emit quite a lot of dust. But also, because the planet here is already relatively close to the main star, and the moon here is sort of not really orbiting too close to the planet, although from this angle it does look like it's close. At some point, it's quite possible that the moon might actually escape into the solar system. Now, okay, it didn't really happen here, so I'm going to try this again, and this time place the moon a little bit farther away, because what we're trying to do here is we're trying to cause the tidal effects from the main star to literally steal the moon. And you'll notice that right here it actually did happen. And so if I enable orbits and show you what the orbits look like, at some point right here, the moon is going to get literally stolen from the Jupiter system and is going to become its own sort of, I guess, planet in a sense. And this is where this story and this explanation begins. And so here, only after a few days, the moon essentially has its own orbit that becomes relatively eccentric. And while this moon is going to start slowly approaching the sun closer and closer, the planet itself might also get swallowed by the sun, or might actually just stay in the same orbit without really any repercussions. So here, what we're going to have now is this very unusual system where eventually the comet is going to start emitting a lot more materials the closer to the sun it comes. And at some point it might even start emitting all sorts of minerals and all sorts of rocks that are not really ices. They're not really things like water and methane, and they might even start evaporating to the point where they're going to create a relatively sort of permanent and long-term cloud around the star system. Now this cloud, as you can see, is going to create quite a lot of dusty formations in the star system, and this will in turn sort of make it look a little bit more dim from a distance. And so what's really happening here, according to the scientists behind this paper, is that this moon is literally being slowly molten and evaporated by the star itself, and all of this evaporated material is what's blocking the view. And the orbit of this moon is very likely very eccentric. And the main reason why the scientists think it's the moon and not the planet that's being destroyed is because they believe that the planet is already gone. They believe that the planet was either swallowed or disappeared in some other way, and it's only the moon that's left here because it was stolen from the planet earlier on. And this leftover here is technically now its own planet, but is slowly being evaporated, as you can see, and is losing mass pretty much constantly. And so this picture right here from the paper summarizes this pretty well. In this new orbit, the exomoon is literally being shredded apart by the radiation from the star, and it creates these dusty clouds that are being thrown out of the solar system, but while at the same time polluting the system, thus creating these dusty clouds that we're looking at. And the clouds themselves are blocking the star, and this is what we're seeing in long-term observations. While the more short-term observations are probably caused by all kinds of other icy materials that are orbiting in this region. In other words, this exomoon is sort of like a very large cometary body that's just spewing out a lot of materials and creating a lot of dust all over this star system, and will eventually most likely be completely evaporated and will probably end up inside the star. But all of this material will probably stay here for quite a long time, possibly 1 million years or so. Which also suggests that we should be seeing even more dimming effects from all of this dust that's being evaporated here, and so this star should not really be getting any brighter. It's probably going to dim even more. And although the previous explanations using comets did explain pretty much most of this as well, it didn't really explain the long-term dimming. And so by having these rocky materials that you see being evaporated here right now, it presents us with a new kind of explanation where all of this rocky material stays in this region. It doesn't get easily dislodged by the solar radiation. And mostly because, just like for example the asteroid belt, most of this material will probably stay here for quite a long time, while more of the icy particles will probably escape and go past the so-called sublimation radius that you see right here, and then eventually reach the areas where they're not going to be very easily visible. And so it might take quite a long time, as I mentioned, possibly 1 million years for all of this to finally stop. But at the same time, this may also suggest to us that we're going to be seeing more of these similar objects. And there are quite a lot of unusually dimming objects out there we've discovered, and maybe this is actually what's happening around them as well. It's going to take a while before we finally can see and confirm all of this, but so far this is an explanation that tackles all of the previous problems really well, while at the same time once again providing proof that we've discovered yet another exomoon, another moon outside of our own solar system. Although technically by current definitions, this right here would not be a moon anymore. This would be a planet, no matter how small it is, simply because there is no other object in this orbit. Which of course implies that the current definition of planets or planetary bodies is not actually that perfect. As a matter of fact, it's very confusing. At the same time, what this study suggests is that exomoons are really common. They seem to be pretty much everywhere. Every major planet out there probably has a lot of moons, and by seeing these effects of a moon on a star system, it will help us understand what's really happening out there in the outer regions of our galaxy. But more importantly, by looking at this dust here and by trying to analyze the molecules, we might be able to determine what the moon was made out of, and of course help us understand what the entire star system might even have inside of it. And although originally we've discovered the star over a century ago, it basically took this long to finally explain what's really happening here. Now, it's definitely not aliens, well, at least we don't think so, there's nothing to suggest that, but it's also something really unusual. I mean, an exomoon being actively destroyed by a star and turned into dust, that's kind of cool. That's definitely the first time we've ever seen this, and it's probably going to be a while before we see this again. Hello wonderful person, this is Anton, and in this video we're going to be talking about a very recent discovery or a very unusual star system that beats a lot of records and creates an opportunity for us to study gravitational waves in more detail in the future. So what you're looking at right here is one of the more famous objects, one of the closest objects to our solar system. This is Sirius B. Sirius system is a star system that's very bright in the night skies. You can see it pretty much from everywhere in the world, and for the most part, most people don't realize that it's actually two different stars. The brighter star is Sirius A right there, but the much more dim partner that it has, known as Sirius B, is actually a white dwarf. And white dwarf is a type of a stellar remnant, or a star that used to be a much larger star but now is a tiny core of that star. That our sun is going to become as well. So our sun is going to be very similar to this. But in a very recent discovery of a paper that was just published in Nature magazine, these scientists discovered a very strange, very unusual, and very exciting binary star where both stars are white dwarfs. But it just so happens that they're so close to one another that they're most likely producing a lot of gravitational waves that we're going to be able to detect with future detectors. Now, right now, the most famous detector is the LIGO detector that was responsible for discovering gravitational waves coming from black holes and neutron stars, but it's not really that strong yet to be able to detect the gravitational waves from two white dwarfs. But we believe that with upgrades and also with an installation of what's known as LISA, that's going to be a space antenna that's going to improve all of this detection, we'll be able to see this and we'll be able to detect these gravitational waves as well. But what exactly did these scientists discover? Well, what they discovered is basically an eclipse in binary. That's when a star that you can kind of see right there, it's very difficult to see because that's sort of what they were looking at, starts blinking. And here the blinks were very periodic and were also very fast. In other words, the two stars that were orbiting here were doing so very quickly. And that's because these two stars were actually orbiting around one another exceptionally fast. The single orbit here takes roughly around 6.9 minutes, or 6.91 minutes if you want to be super precise. And that means that in these 6.9 minutes, that's what you see. You see an actual star orbiting around the other star and most likely also losing a lot of matter that we were able to recreate here in Universe Sandbox. So these unusual binaries are not really uncommon, but having such a quick binary or such a quick orbital period is very strange, and also basically now is a record holder for the fastest orbital period as well, and also for the fastest orbital speed. With the less massive star that's actually bigger than the other star, moving at close to about 1000 kilometers per second, or actually over 1000 kilometers per second, when they're in the closest part of their orbit. Now, these two stars are both white dwarfs, meaning that back maybe billions of years ago, these two stars were very similar to our sun, and they were partners and they were orbiting around one another, eventually losing their shell and becoming these cores that we know as white dwarfs. This star that's bigger is about 20% the mass of our sun, and with white dwarfs, the more massive the white dwarf, the smaller in size it gets. So this here is a little bit larger, it's about 60% the mass of the sun. And it's actually what our sun is going to become eventually as well. It's going to be very similar to this star. And these two objects have a name that's sort of difficult to say, but it's ZTF J5039 plus 5027. The larger or the more massive star, as you can see right here, is actually absorbing the mass very slowly and is collecting around itself. And the mass is coming from its partner. So basically, because of the tidal interactions, when they're closer to each other, it sort of steals some of the mass. And eventually, this mass theft is going to increase even more dramatically, where possibly within the next million or so years, the two stars will come close enough to each other to have two possible sort of interactions and two possible resolutions. One of these resolutions will create a single star, And that's something that might happen if this mass transfer is not stable. In other words, if it happens in unpredictable sort of chunks. And so if the mass transfer is not stable, what's going to occur here is a single white dwarf that's a very rare white dwarf known as R Corona Borealis variable. These are somewhat unusual white dwarf-like remnants that also have a strange property of dimming really unpredictably once in a while and then going back in brightness again. This is something that's not very periodic. This is something that happens for unknown reasons, and we still don't really understand these remnants really well. We just know that they're the result of a merger between two white dwarfs and produce these super unpredictable patterns that we still can't really explain very well. However, if this transfer is more stable, in other words, if it's not really hectic, if the actual mass transfer is constant, at some point these two stars will separate a little bit, creating a very stable binary that's actually one of the weirdest stars that you can find in Space Engine as well. And this is a type of a binary star known as AM Canum Venaticorum. These two stars are basically two remnants of white dwarfs, with one star constantly receiving matter from the other. In other words, it does look something like this, but a lot more complex, with the actual mass transfer becoming almost like a stream of particles leaving the less massive object, arriving to the more massive object, and creating a sort of a very constant flow. And in some sense, this is maybe what it looks like. This is from Space Engine, with two white dwarfs orbiting around one another close enough to have an actual stream of particles that you can't really see here. It's very difficult to see, but at the same time creating a lot of energy. As you can see, they're also, in this case, creating the astrophysical jets and a lot of gravitational waves as well. In reality though, it's obviously a lot brighter than this, and it does look quite magnificent and has always created a lot of mysteries for the scientists. We still don't really understand what's really happening around these two white dwarfs as they transfer this energy, and also how long they even last. And the way we discover these stars is because they also show this unusual variability, and they do very periodically change brightness. So a very beautiful and very interesting system, and this is kind of what the white dwarfs we've just discovered may become as well. However, for now we don't really know what its eventual fate will be, because it still has quite a few thousands of years to go. As a matter of fact, it will take it approximately 130,000 years before they arrive at a distance that's close enough for them to start transferring mass very constantly or very unpredictably. So it will be at least 130,000 years before their orbit decreases to about 5 minutes from 6.9 minutes, and before we can officially start predicting what their fate will be. Obviously, in 130,000 years, humans might not be around anymore, although you never know. We might actually persevere and become super star-traveling race that might even get to visit these objects as well. But nevertheless, the discovery of these objects is very interesting, because this is something we don't really see very often. Two stars so close together. Now, how close is this? Well, remember, a single object like a white dwarf is only about the size of a planet like Earth. So this object is very similar to Earth. So altogether, this orbit between them is comparable to an object like Jupiter in size, or even smaller than that, even Saturn. So you can technically fit all of them into a gas giant. And these objects together form a mass equivalent to almost the mass of the Sun. They're also slowly moving closer and closer toward each other at roughly around 26 centimeters per day. That's almost a foot per day. And what's really interesting here is that despite there being a lot of energy being produced through their interaction, we don't seem to see any X-rays or any other very powerful radiation being produced, which is unusual. We expected to see something like this. And one of the possible explanations is that, well, maybe the matter here accretes a lot slower or in much wider area, instead creating a lot of ultraviolet and a lot of visual light instead of X-rays. So there is still some mysteries here. There's still a lot to discover and learn about these two objects. But most importantly, there's actually a very high chance that in a few billion years from now, this is kind of what Sirius stars will become as well. It's quite possible that because the larger star is already a white dwarf that's going to last for billions of years, the second star, that's currently very similar to our Sun, Sirius A, will also turn into a white dwarf, eventually creating a white dwarf binary very, very close to our own solar system, and that binary is probably going to stay in our vicinity for a very long time. It will also generate a lot of energy and at some point might become catastrophic. So in a few billion years, Sirius stars might actually cause some sort of a danger to our system, but by then we don't really know if Earth is even going to be around anymore. And by the way, this particular system is not really dangerous to us because it is really far away. It's almost 8,000 light years away from us, so we have nothing to worry about even if it goes supernova. But anyway, on that note, that's really all I wanted to show you in this video. It's a pretty cool discovery of two very interesting white dwarfs orbiting really close to each other and producing these really unusual effects that will one day cause them to become a single very unusual star with strange variability, or instead become two stars very similar to this right here, the system of two white dwarfs that you can find in Space Engine if you look up AM Canon. Hello wonderful person, this is Anton, and in this video we're talking about FU Orionis pre-main sequence stars, or I guess as you and I would call it, baby stars. We're going to talk about a recent study that clarifies what happens to really young stars and how they manage to grow really fast. Welcome to What the Math. But our story begins right here. You're about to see what's known as McNeil's Nebula. McNeil's Nebula is a discovery from early 2000s when an amateur astronomer with a relatively small 3-inch telescope whose name was J. McNeil discovered this unusual thing that you see on the screen. Here's a slightly more realistic picture of what he actually saw. This was back in 2003. And this was the first such discovery ever. And then, slowly, with every year, this started to disappear, eventually becoming practically invisible, and as of 2019, it's gone completely. And so, as you can imagine, this raised a lot of questions. And today we know that what we've discovered was the so-called pre-main sequence star, also known as FU Ori, or FU Orionis, which represents the first such discovered star. So it kind of looks like this. This is essentially a baby star. This is a very small, very compact object that is slowly gathering mass from the nearby disk that orbits around it. I actually tried to create something similar in Universe Sandbox. It doesn't look as good, but it's going to serve its purposes for this video. So there is our FU Ori, and there is that disk orbiting around it. And based on the study that you can find in the description below, we now are able to explain what's happening around those objects a lot more accurately. Because this particular study was able to observe 25th such object using quite precise observations in both infrared and also visual light. And before I explain to you what they observed, what you need to understand first is what's really happening here. So we have this object in the middle, and it has these two poles that are essentially really powerful X-ray emission sources. And that's because the star itself is very young, but it's also very electromagnetically active. And it's actually absorbing mass through these hot spots and slowly grows in size. But the problem is that it's not growing fast enough. If this was the only thing that was happening here, unfortunately none of these stars would look like this. They would not really gain enough mass to have mass that we observe. And so for the longest time, scientists were not sure how exactly is it that stars are able to get so massive so quick. And they've coined a term known as FU Ori events. So these FU Orionis events are kind of like the growth spurts that some people experience when they're teenagers. Suddenly, a star can grow by a tremendous amount very quickly. And we believe today that these particular growth spurts, which is exactly what we observed very recently, happen approximately every year or so and can last from anywhere like a few decades to maybe 100 years. And in total, a star can experience maybe 10 or 20 such events over its lifetime, and every single time it experiences an annual growth by absorbing a large amount of mass that I'm going to show you in a few seconds. But we also know that these stars are very powerful sources of X-ray radiation because these stars spin really fast, and they spin faster than the accretion disk around them, and this sort of entangles a lot of the magnetic lines, and once in a while these magnetic lines snap and you experience a very powerful X-ray emission, which is usually how a lot of these stars are found. But at the same time, they also increase in brightness, and this is what we didn't really understand at first. And so this recent study kind of analyzed this, and they discovered that for most of these stars, the mass that orbits around the actual accretion disk once in a while starts clumping together, forming these relatively large clumps of matter like you see right here. This one actually is in the shape of a moon because that's how the universe sandbox generates these objects. And these clumps, when they're created because of the relatively high density of the accretion disk, slowly start moving closer and closer and closer to the actual star. They've discovered that it takes it about a year and a half to make it all the way from approximately 1 astronomical unit to the center of the newly formed star system, and eventually all of these objects, like the one you see right here, will come so close to the star that they'll get swallowed, and when they get swallowed, a tremendously large outburst of energy is created that resembles something like this. It's a very bright and very powerful event, but all of this starts with the actual star absorbing a lot of matter very quickly, and all of this matter suddenly falling into the star, while at the same time creating a large explosion and increasing the mass of the star quite dramatically. And right after this it goes back to its original state and continues until the next such event. And the scientists in this paper discovered that such star can usually absorb approximately 1/1000th of the mass of our own sun in about a year. So these are really fast, extremely fast growth spurts. It's basically like absorbing over 300 masses of Earth every single year, but all of this as a kind of a single event, not an event that lasts for a long time. In other words, it's equivalent to the mass of Jupiter being absorbed every single year. For a pretty long time, for at least 100 years, every year you get these events, and then there's approximately 15 to 20 of these events per lifetime. So by the time that the star is done doing this, it usually acquires a lot of mass and increases both in size and mass quite dramatically. And so here we can actually even feed our newly created FU Ori star the Jupiter that we just put here, and this is kind of the recreation, although not a very realistic recreation, of such events. So here you can see that as soon as this happens, even in the simulation that we've created, there's a tremendous outburst of energy. And this is what we recently saw, and this is what the paper discussed. So these events are actually quite rare. As a matter of fact, we've only discovered 25 of such stars, and only I believe 13 of them have been observed doing this. So because these events don't last very long, it's very rare that we'll be able to find them. And being able to study such events will help us understand how a typical star is created and how it goes from being just a dust cloud to being an actual fully developed star with a lot of planets and a lot of other stuff orbiting around it. And a lot of the star evolution we already understand quite well based on the observations from other star systems, but this particular period in stars' life is still a bit of a mystery to us, especially because the observations that we've seen so far are quite mysterious. Like, these outbursts were not actually explained for a very long time until relatively recently. And so hopefully one day we'll see more of these young baby stars that will help us understand how our solar system was created, and maybe even where all of the gas that it was made from came from, because that way we'll be able to find very similar, possibly even identical star systems to our own that may even have a terrestrial planet around them. But until then, that's all I wanted to mention in this video. I just wanted to talk about baby stars. And honestly, that would probably make a pretty good song as well. Baby star to-to-do-do-do. Yeah. Maybe I'll go pitch that idea to that Korean company that made the Baby Shark song. Hello wonderful person, this is Anton, and this right here is yet again one of the very mysterious stars that was recently described and explained by science. Today we're going to be talking about this system known as NGTS-7 and what the scientists discovered here for the first time ever. First of all, what you're looking at is a very interesting binary system. Well, actually, this is not the binary system itself. This right here is a brown dwarf that you can see in front of me that orbits an M-type star, also known as a red dwarf. These stars are the most common stars in our solar system, with the nearest one being Proxima Centauri. If I were to zoom out here, you'll see that these two objects orbit next to each other, relatively close to each other. And they do so in a very unusual manner. But let's not rush into things, and let me first explain to you why this system is so unusual. So first of all, this is actually kind of far away. It's roughly around 400 light years away from us, and when the scientists were just looking at the system from a distance, because these are red dwarfs, and are not generally really bright, what they were seeing was essentially something like this. It was a single star. But some scientists decided to zoom in a little bit, and they realized that there was a binary star system here with a very large brown dwarf orbiting around one of the stars. In other words, it looked something like this. We have the main star, NGTS-A, orbited by a relatively large brown dwarf with a mass of roughly around 62 to possibly even more masses of Jupiter. Then we have the partner star, and the partner star, known as NGTS-B, orbits at a distance. And altogether this creates a very interesting and very unusual phenomenon. And this is kind of what the scientists were confused about. And this is actually why they decided to zoom into the star to begin with. It's because it was blinking at them in a very predictable pattern every 16.2 hours. This is how they discovered the brown dwarf. But the mystery did not stop there. The mystery was actually in seeing other unusual blinking patterns every 16.2 hours as well. In other words, something else was also causing the star to lose luminosity a little bit. And they suspected that this something may have been the beautiful spots that you see on the surface of the star, these so-called sunspots. These are of course formed by the incredibly strong magnetic field on the surface of the star. But to have such strong magnetic fields, to have such strong magnetic lines, this star has to be spinning really fast. And that's when they started to realize something incredible was happening here. And what was happening here was that both the star and the brown dwarf were tidally locked to each other. They were literally always facing each other, and this is something that we've never seen before. That's because this brown dwarf is massive enough to have accelerated the rotation or the spin of the star. It made it spin faster over time, and what's even more interesting is that because of that other object, the faraway but lonely object known as NGTS-B, it's slowly causing the brown dwarf to fall into the main star, thus accelerating its rotation even more. So in other words, what's really happening here is described by a so-called Kozai phenomenon or Kozai mechanism. You can check out more about it above my head. But in short, that other star is causing the brown dwarf to slowly make its way closer and closer to the star. And obviously it's going to lose a lot of mass in the process, as it's already doing. But here, every time it moves closer and closer, it's going to accelerate the rotation of the star itself, and this in effect will give it even more magnetic field. It will become even more magnetic, flare up even more than it's already doing, and eventually will become one of the most magnetically active M-type stars in the galaxy. In other words, eventually this effect may cause the star to spin so fast that it will either fall apart or become a ridiculously powerful source of really powerful flares. And today we believe that in about 10 million years, this planet, this brown dwarf, will probably eventually come so close to the star that it will either fall apart or get swallowed completely, but as it does so, the whole system will be spinning ridiculously fast. Let's try to simulate this here, and let's see what happens if the planet comes really close to this object. So this discovery suggests to us that there are planets out there that are massive enough to influence the behavior of a star, to influence its rotation, and most importantly to cause it to be more active than other stars. This star's activity is actually influenced by the very massive brown dwarf next to it. And we've obviously never seen anything like it, we couldn't even imagine this happening, and most importantly, we now believe that other stars out there may have been influenced by their own planets, and if they have a very fast rotation, maybe this is actually what happened in those systems. Now, our star, the Sun, is a very slow rotator, and so maybe, just maybe, the explanation for why it spins so slow compared to other stars is because of something similar. Maybe there was a brown dwarf that actually slowed it down instead of accelerating it. Now, that's just a speculation right now, but you never know. Now that we've seen that it's possible, we know that it could happen in other systems. And because this star system is actually kind of young, it's only about 50 million years old, so it's technically a star baby, or two babies, we know that eventually it will evolve even more, And okay, here we go, and maybe even this will occur as well. Maybe the star will fall apart completely because it's going to be spinning so fast, with the partner right here possibly getting kicked out of the system, or possibly absorbing a lot of this matter and creating its own miniature star system. So we don't really know what's going to happen to this object in the next 10 million years, but what we do know right now as a fact is that it seems that some planets are so massive that they can influence the behavior of stars that they orbit. And being able to tidally lock a star to yourself is actually a very interesting achievement. And because this is the first time scientists have discovered something like this, it means that now we can potentially explain some of the unusual observations out there in the universe by using this specific mechanism. Now, it's very likely that we might not be around anymore to see what really happens to the star at the end, but we might see some other similar stars where this process has already happened, and so we might be able to discover something in the next few years that will help us explain how all of this evolves over time. But until then, that's really it. This unusual system, an unusual star, and its unusual brown dwarf are definitely something that scientists didn't expect to find. Hello wonderful person, this is Anton, and in this video we're going to be talking about a discovery of another really strange star that's kind of reminiscent of the Tabby star. The star that seems to be unpredictably dimming itself once in a while, but there's no explanation for why it changes its brightness. By now you have probably heard of Tabby star, the star somewhere out there that created a kind of a buzz in the news because some scientists suggested that maybe it's an indication of an alien civilization. And all of this was caused by the fact that the star actually dimmed quite a lot and was doing so without any real patterns. By now though, most of these studies have kind of debunked this idea of the so-called alien megastructure, and most of these studies suggest that the dimming of this particular star was probably caused by somewhat irregular, very large cometary bodies orbiting in the vicinity of the star, but with peculiar orbits. So even though most of us would love to believe that it was some sort of an alien megastructure, it's very likely not, unfortunately. Even the chances of this being some sort of a large planetary collision or planetary destruction, that was one of the explanations, is just not really there. Mostly because these events are so rare that detecting one so quickly would be quite unlikely, and at the same time we just didn't really see the things we expected to see, such as the dust clouds. But it just so happens that another paper showed up very recently showing an even stranger occurrence out there in the universe. Another pair of stars known as Epic 24, okay, you can see the name, it's kind of hard to read so I'm not going to even try, but basically also known as HD 139139, much easier name to pronounce. And this particular binary star exhibits an even stranger and, what's really interesting, super hard to explain pattern. So what exactly did the scientists see? Well, first of all, this is a binary system unlike Tabby star, so there are actually two stars here, creating a lot more unpredictability and a lot more variability in potential orbits. But what they saw around one of these stars, and we don't actually know which one because it's kind of hard to see that, they've discovered that this particular star, when going through the Kepler-2 data, changes brightness as well. And what's really interesting about how it changes brightness is that it did so 28 times in a very similar fashion as if it was the same kind of object passing in front of it, but this was done completely randomly, with no observable periodicity. In other words, it's as if something was moving in front of a star and then just kind of doing so repeatedly whenever it wanted to. So this is when this particular study gets even more interesting because we have no idea how to explain this. But I guess to start all of this, let's visually create the system just so we can actually visualize what's going on here. So first of all, the main star, known as HD 139139A, is very similar to our own sun. It's a G-type star, just a little bit brighter than our sun, but at pretty much the same temperature. The partner is a little bit smaller. It's what's known as a K-type star, but still bright enough and massive enough to be somewhat similar to the sun. They're also a lot farther away than this, but I placed them a little bit closer just for the sakes of the simulation. Now they are orbiting around one another, and Originally, we didn't really detect anything from this system. This is actually coming from the now defunct Kepler-2 telescope that still has a lot of data available, but because there's so much data, it's very difficult for a scientist to analyze it. So instead, they rely on what's known as citizen scientists. Basically, this is how the Tabby star was discovered as well. So someone out there, an actual just regular person like you and me, using the NASA Citizen Science program, were kind of going through data and trying to see if they could find more planets. And usually this is done through a kind of a mini game to make it a little bit more interactive. You can actually check out some of them on the website known as Zooniverse that has like hundreds of these projects that are usually presented in a game-like format, or at least more interactive, where you can help scientists analyze data from anything like animal research to basically space sciences. There are currently 108 projects here, anything from arts, biology, climate, and so on. And one of these programs was basically Planet Hunters. And that was of course done to look at the Kepler's data and try to discover some more planets. I think a few years ago I actually tried this for fun myself. I didn't really find anything, but it was interesting. It was actually kind of cool to be part of the discovery. And so these citizen scientists discovered something peculiar in the Kepler-2 data. They discovered this unusual dim that was happening around the binary system, which led to them contacting scientists and showing them that this is a star they really needed to take a look at. Which is what the scientists behind this paper did, and they discovered quite a lot of these very peculiar, very unusual dips that they just couldn't explain. And all of these dips, as you can see, were kind of similar, suggesting that a very similar type of a planet or an object or something similar to a planet passed in front of those stars. Now, the first assumption was obviously that it was a planet, and in this case, if this planet was in front of the smaller star, it would represent a planet similar to Earth in size. So this would have been, let's place this here, this would have been an Earth-like planet passing in front of the star. However, if this was around the larger star, it would be equivalent to Jupiter in size because of the dip we observed. So it was basically 28 Earth-like passages or 28 Jupiter-like passages. But here's where it gets interesting. None of this was periodic, none of this was repeated. All of this was completely random. So it's as if this particular star system had 28 exactly the same planets in a very peculiar orbit. Which I guess in some sense is possible. Maybe there is actually, like, let's just be hypothetical here and suggest that maybe there are 14 Jupiter-like planets orbiting around the larger star and 14 Earth-like planets orbiting around the second star. But that of course presents us with a new problem. How can all of these planets be exactly the same in size? That sort of defies all logic and defies what we're observing out there in the universe. And because these 28 dips were detected in a period of about 87 days, that's what makes it even stranger. It's as if these objects passed in front of these stars within only a 90-day period, within 3 months. Now, if you look at the data, you can see that they weren't really exactly the same size. They were slightly different by just a little bit, but they were similar enough to be either same planetary objects or same sorts of objects with very, very similar parameters. And it's actually worth reading this paper just to see how they analyze potential explanations. They actually go through pretty much every scenario. The disintegrating planet scenario, which is disproved pretty quickly. Various cometary objects, which is how Tabby star was explained. That's also not the case here. And even some of the more exotic explanations, such as, for example, maybe this is some sort of an unusual, let's just try this here, some sort of an unusual circumbinary planet, and that refers to the idea of a planet that orbits both stars at the same time. And in this case, well, it just wouldn't explain how we would see this so quickly. So yeah, you could have these unpredictable dips if a planet was circumbinary and orbited both stars, but it was just too quick. At the same time, they also tried to explain this by maybe having really unusual and really gigantic sunspots that appeared on these stars and caused the brightness to decrease. Maybe these sunspots appear because of some sort of interaction between stars and are large enough to decrease the brightness, which I guess in some sense is possible. But this would also imply that we should be seeing this a lot more often out there in the universe, and we just haven't seen any similar effects anywhere else except for this particular system. Now, they don't really mention the megastructures in this paper, but I'm sure someone will, so we don't have to worry about that. But honestly, this wouldn't really explain anything because even a megastructure would have periodicity. These dips or these observations really don't, so not the best explanation. And the scientists end this paper by basically saying one thing. The reason for this paper is not to try to explain what's happening or try to present some sort of an unusual alien explanation or scientific explanation, but to bring this star to our attention, to try to show us that something out there is happening and we just can't explain it, so please someone explain it, because otherwise we're going to be stuck with another unexplained phenomenon that's just not cool with us. It's not cool. We need to try to find a way to present this idea in scientific terms that doesn't involve aliens. And if it is aliens, well, then we need more solid proof for that as well. Right now, this is literally all we know. Unusual dimming patterns, very unpredictable, very unexplainable. And this is what makes this paper probably one of the more exciting findings of 2019, except for, of course, the black hole picture that we took a few months ago. But this here delivers to us another unusual phenomenon that science currently doesn't really understand or cannot explain very well. Because the scientists in this paper analyze this in a lot of detail, and they even try to simulate the circumbinary planets that I previously mentioned, and try to see if they could create a similar observation with these unusual planets that orbit both stars. But they were able to create only 4 such observations, not 28 like we saw in real life. So definitely something that we need to look into and try to explain in some way or another. And this of course means that in the next few years we're very likely going to be looking at the star in more detail using other telescopes to try to see what's really happening here, just like we did with Tabby star. And I'm pretty sure that this star is going to hit the news really soon, again, just like the Tabby star, and we'll get some really cool name. Now we don't really know what name they'll pick eventually and what nickname will stick to the star, but even the main name, HD 139139, is pretty easy to remember. And by the way, fun fact, there's another really interesting tidbit about the star that these scientists mentioned. Apparently, if you were to look at our own star system from here, and this is by the way at a distance of roughly around 350 light years away from us, you would actually be able to see our planet Earth passing in front of the sun. In other words, if you were to use a powerful telescope and were to zoom in on our star system, you would actually see Earth pass in front of the sun and create very similar dips to what we observe when we look at stars, or when we used to look at stars using Kepler telescope. So in other words, if the aliens in this planetary system, assuming of course there are aliens, look into our solar system, they'll see Earth passing in front of it and be able to identify it as a planet. Now this obviously has nothing to do with what we've detected in this star system, but it is a very interesting fun fact. And anyway, on that note, that's all I wanted to mention in this particular video. Check out the paper I mentioned in the description below, and maybe even consider joining these citizen scientists and look into projects like Zooniverse, where you can contribute to science by doing these fun little mini games that basically analyze data for the scientists. Hello wonderful person, this is Anton, and what you're observing is what a supernova is supposed to look like in real time as it expands after a star exploded. But in today's video we're going to be talking about a very special supernova that we just observed for the first time in history. So one thing that I think all of us know about supernova is that it's basically a very large explosion, and it ends up releasing a tremendous amount of matter, creating very beautiful clouds that we usually refer to as nebula. Now these so-called supernova remnants, or these tremendously large beautiful clouds, are very important because that's what other stars will be made out of, including of course our sun, and well, technically you and I were made as a result of these supernova a long time ago. But the supernova we're talking about today is exceptionally rare and was only basically hypothetical until now. But before we talk about this, so like I mentioned, all supernova end the same, but most of them start completely different from one another. We have different types of supernova based on their origin. And just to give you a very general breakdown of all of this, and this is not really that detailed and is only meant for the sakes of the length of the video, we have the supernova known as type 1a, which is often caused by white dwarfs. This is Series B, the closest white dwarf to us. And when this particular white dwarf reaches a certain limit of its mass, it explodes, creating type 1 supernova. We can do this manually by pressing the explode button, and there you go. So there is a type 1 supernova, but we also have type 2 supernova, which are almost always caused by these tremendously massive stars, usually at least 15 to possibly 30 masses of the sun, that are just too massive for their own good and eventually just can't handle it anymore and reach a point where they start collapsing because the inside of the star cannot support all of this mass anymore, and then they also explode, but this time it's known as a type 2 supernova. These are usually a lot more massive in terms of the actual material released. And so here we're going to let this go, and you'll see both supernova happening side by side. Now, there is another type though, and that type is a little bit different from both of these. It's known as the Pair-instability supernova, and I think the best way to explain this is to actually take a look at this picture. So in very large, very massive stars, specifically stars between approximately 130 to maybe 250 masses of the sun, but not more than that and not less than that, at some point the inside of the star becomes so energetic and starts producing so many gamma rays, or basically very powerful radiation, that some of these gamma rays start hitting the actual molecules inside, and then as a result of this collision they start producing, well, technically matter and antimatter, usually electrons and their opposites, positrons. And so in other words, these gamma rays start being sort of taken away from the equation and disappear, creating matter and antimatter. And as more and more of these gamma rays disappear, the actual ability of the star to support itself from collapse starts decreasing quite dramatically. In summary, these gamma rays that were responsible for keeping the star from collapsing now start disappearing suddenly, and the star itself starts slowly collapsing, and at some point reaches such a tremendously large pressure on the inside that the thermonuclear energy inside increases dramatically, like to the point where it just can't handle it anymore, and the star just overcomes its own forces and explodes with a spectacularly massive and very, very powerful explosion. But here's the thing though, although normally a star would leave something behind, this particular explosion that I'm going to try to initiate here is going to leave nothing behind. There's going to be no black hole, there's going to be no neutron star, nothing left but empty space, with all of the 130 to 250 masses of the sun being released as a tremendously powerful explosion, one of the brightest and most powerful explosions we can imagine. And we've always believed that in the beginning of the universe, pretty much all of the supernovae were like this. All of the really massive stars, these so-called population 3 stars that existed 13.5 to 13.8 billion years ago, all of them exploded in these very, very powerful, very bright clouds. And all of them disappeared completely, releasing everything into the outer space, and all of this then started creating the second generation stars, the population 2 stars. And so now we come to the discovery of the year, I guess, in a sense, because we finally discovered such an unusual supernova. This paper from the Astrophysical Journal talks about the analysis of the supernova from a few years ago, and here you can actually see the image that they published as well. This is in 2014, there's basically almost nothing, and this is in 2018 where there is a very, very large, very prominent explosion and with a lot of luminosity comparable to a nearby galaxy. And the scientists behind this paper explain this as, well, essentially very likely the pair-instability supernova I just described to you. Basically an extremely large and extremely massive star created such a large and such a bright explosion that it's visible from really far away. Now, what's interesting is that we've always predicted that these types of pair-instability supernova would probably happen in relatively low in metal galaxies, basically galaxies that mostly have hydrogen and helium, not so much anything else, and also possibly in dwarf galaxies that are really ancient. And this is exactly what we see here. A very ancient dwarf galaxy, relatively low in metals, and it just so happens that very close to it, only about 54,000 light years away from it, we get to see our prediction come true. The pair-instability supernova that we knew might have existed, we just have never seen one. Until now. Now there are a lot of really interesting discoveries coming from this particular supernova, and one of them is that, unlike other supernova, this one is really taking its time. Most supernovae disappear within a few weeks, maybe a few months. This one has been going on for a few years now, and the scientists believe that it's going to actually continue doing so for a very long time. And that just shows you how extremely powerful and how extremely massive this supernova is. And we also think that all of this started with a star that was very similar to what you see on the screen. And here is our sun for comparison, including of course our beautiful planet Earth that seems completely and totally insignificant. So this tremendously large star was probably over 100 masses of the sun, and it only lived for a few million years, because such large massive stars don't usually live very long. So even when our ancestors started to walk on 2 feet, this star didn't even exist yet. It's a relatively young star, and it only lasted for maybe 3 million years or so. And when this star went supernova, a very large fraction of its mass was instantly converted first to an isotope of nickel known as nickel-56, and then to another isotope almost right away, only within a few weeks. Here's actually an image from Max Planck Institute for Physics that shows you how nickel-56 only after about 9 days converts to cobalt-56, and then after about 111 days converts to the final product, which is iron-56. And so we expect that most of the stuff in this particular supernova will become the isotope of iron that you see right here. But there are a lot of unanswered questions here. One of those questions is, well, in regards to the location of the supernova. We expect these massive stars to be born inside of a galaxy, possibly close to a dense cluster of stars. But this one is really in the middle of nowhere, really far away from the galaxy. And, well, we don't really know why. On the other hand, we can't really explain why this object is staying bright for so long. Although there is one suggestion, and this suggestion implies that even before the supernova, the very massive star must have been ejecting a lot of materials outside. And when the supernova happened, all of this energy caught up with this material and is now making it shine even brighter than before. In other words, it's basically like we have our first wave of material being hit by the second wave, and that's causing the brightness that we're observing now, which means that this brightness will stay around for a pretty long time. But most importantly, because this particular supernova is so far away from the center of the galaxy, it's going to be very easily visible to us for many years from now. It's simply just in the middle of space, so we'll be able to detect even when it's ridiculously dim. In most galaxies, the actual brightness of the galaxy covers the supernova. Not in this case. In this case, this is probably going to be the prime destination for all of the supernova studies in the next few years. And I'm sure in the next few years we'll be able to discover a lot more exciting and really interesting things coming from this particular supernova. We even think that one of the nearby stars to us might one day, hopefully not too soon actually, produce a similar supernova. I'm talking about a star known as Eta Carina, that's actually in a kind of a same mass range that should be producing the so-called Pair-instability supernova. Hello wonderful person, this is Anton, and in this video we're going to be talking about a discovery of what seems to be one of the fastest stars moving through our galaxy, beating a lot of previous records. This star that we're going to talk about today also resolves one of the mysteries of our galaxy, and also how these stars acquire this speed, and you may have seen just how in this particular simulation. And the star that we're talking about is right here on the screen. This is just a simulated version, mostly what it's going to look like when it leaves the galaxy. It's still inside our galaxy, but it's moving at a speed of roughly around 1700 kilometers per second. In comparison to that, our sun is moving at roughly around 230 kilometers per second around the Milky Way. So the velocity is large enough for the star to escape the galaxy, and even much higher than that. Now, we've discovered some really fast moving objects before, but what's really interesting about this particular star, apart of course from its really high velocity, is that it's actually a relatively normal star. It's a main sequence star, about 2.3 masses of the sun. That's also most likely significantly larger than Sun in size. Here's Sun in comparison. And this particular star, unlike other stars we've discovered, is basically very different from other hypervelocity stars we've found so far, which are usually either really bright and really massive like O-type stars, or are remnants of stars such as white dwarfs. Now, this star is about 500 million years old, So it means that it's not really that old, and it probably got all of this velocity relatively recently. And according to the calculations that the scientists have in this paper that you can find in the description below, and the paper is called The Great Escape, the star itself probably escaped from the central part of the galaxy roughly around 4.8 million years ago. And in about 500 million years from now, it will most likely turn into a very beautiful planetary nebula, something very similar to what you see on the screen, but this nebula is going to be moving at a super high velocity of roughly around 1600 kilometers per second. So we're going to see this unusual bright cloud moving away from our galaxy. So all of this will of course be very interesting to see, but that's in the far future. But now, what do we know about this star? Well, the one interesting fact about it is where it actually came from. Having integrated the actual velocity vector, the scientists discovered that, not surprisingly, this star came from somewhere right here, from the central region of our galaxy. And there are only two possible ways it could have gotten kicked out of there, with one major one being the supermassive black hole Sagittarius A star. So this star is presenting us with essentially an explanation and a confirmation that supermassive black holes like the one you see right here can quite easily kick out a star out of a galaxy. Now, the other explanation involves a slightly hypothetical concept of intermediate mass black holes that was probably swallowed by this black hole, and the interaction of that intermediate black hole may have actually kicked out many stars from here. But until we discover more similar stars to the object that the scientists are referring to as S5HSV1, we're not going to be able to confirm that idea. For now, we think that it was the Sagittarius A star that forced this beautiful object to escape our galaxy, or to basically put it on a course to escape the galaxy. Now, what does S5HVS1 stand for? Well, S5 is actually a very large survey of all of the stars in the southern hemisphere. It's called S5 because of 5 S words in there, and its main purpose is to actually try to discover as many of the stellar streams as possible. You may remember from previous videos, stellar streams are these absolutely beautiful formations around our galaxy that were formed when our galaxy most likely absorbed and consumed other smaller galaxies. These are essentially like the leftovers, kind of forming rings and various shapes around the galaxy. We've discovered quite a lot already, and we were trying to discover even more with S5, but instead of that, what the scientists behind this paper discovered was, of course, this unusual fast-moving star. However, normally, the hypervelocity stars gain their velocity through very powerful supernova in binary systems, where one of the stars, or even both of the stars, receive this push from the galaxy and eventually go on their major path across the galaxy, away from the galaxy, into the intergalactic space. In this case, there was no supernova, and the star is completely unaffected. It may even still have its planets. We don't really know, it's too far to see, but it might. And we are pretty sure that it was kicked out by the supermassive black hole, but how exactly could that happen? Well, this is where a really interesting phenomenon known as three-body problem comes into play. We can actually very easily simulate this in Universe Sandbox by first removing the collisions, and then let's actually do this with our Sun and maybe 2 planets, like for example, let's do Earth, that's going to be orbiting around Jupiter. And so here, we're going to also enable orbits just so you can see the evolution of all of this. The three-body problem refers to basically 3 bodies with various masses and how they start interacting with one another and create these really complex gravitational interactions. Now, you'll notice that this is actually a good example. Earth used to be around Jupiter, but now it got kicked out of this system. But if I accelerate this more, eventually through various interactions with one another, they're actually going to create really complex patterns. And these patterns will, at some point, may even reverse the actual direction of the orbit, or may completely kick out one of the objects from the system. So here, if I accelerate this, eventually the three-body problem becomes really complex. Now, we believe that this is kind of what happened with this particular star, and it used to have a smaller in mass partner that was probably around the same distance in orbit as Mercury is today, maybe even closer than that, and eventually something happened to it, and as the stars moved closer and closer to Sagittarius A star, they experienced the three-body problem effect, and one of them may have gotten swallowed, while the other received a huge boost from the gravitational interaction, and thus essentially left the system at really high velocity. Now, according to the calculations, for this to happen, and let's actually erase this. Yeah, you can try this yourself. Three-body problem is a super fun experiment. You never know what's going to happen. It's very hard to predict. But anyway, what happened here is that as the star S5HVS1, and by the way, I forgot to mention, HVS just stands for hypervelocity star. 1 is obviously the first one in this particular survey. Lost its partner, and as Sagittarius A star that you see right here gave it this boost of velocity, it literally started leaving the system at roughly around 1800 kilometers per second, and its velocity hasn't really decreased much since then. All of this, of course, happened because of the absorption or because of the loss of its partner, but scientifically what happened here was a huge transfer of kinetic energy from the orbital energy that used to be there to the star itself, and through this loss it acquired as much energy as, well, I think the best example comes from the scientists themselves. If our Earth were to receive this much energy, and here's our Earth for comparison, it would literally be shot out of the system at roughly around 0.997 speed of light. 99% of the speed of light. It would be ridiculously fast. But if a star acquired as much kinetic energy, it would be shot out at approximately 1800 kilometers per second. Our Sun would obviously get more because our Sun is a much less massive star. So this is how the hypervelocity star was born, but this study is really interesting in that it explains that all of this was almost definitely because of the interaction with Sagittarius A star, but also that it comes from a very specific region around galactic center where we know that around 500 million years ago many similar stars were born. It was actually in the central region of very young star formation where roughly around 500 million years ago many different stars were made, and were made in a very specific location with very specific orientation. And it just so happens that if you trace back the motion of S5HVS1, it happens to fall in this specific region, suggesting the origin was from there. So far what we can see here is a kind of a history and a timeline of what happened to the star. It was born with a partner roughly around 500 million years ago, approached a little bit too close to the central region where the supermassive black hole is. The supermassive black hole dislodged the orbital parameters and captured its partner while releasing the main star at a very high velocity. And eventually it made its way across the galaxy for about 4.8 million years. Now, how far did it travel? Well, multiply 4.8 million years by 1800 or 1700 kilometers per second. A lot of kilometers. Although I think most people are not going to do this and probably will be too lazy to calculate this, so here's the answer: 27,000 light years. Which is ironically the same distance of Earth to the supermassive black hole as well. That's just a coincidence though. But anyway, on that note, that's all we know about this particular star for now. The most exciting part of the study is that if we discover more similar stars to this, then the alternative theory might make more sense. The alternative theory being that it's very likely all of these stars were kicked out by an interaction between the supermassive black hole and a smaller intermediate mass black hole that was absorbed by the larger black hole in the middle. And that would be a lot more impressive. If we can discover more similar stars, similar to S5HVS1, in a kind of a similar motion or similar composition or obviously similar age, that would make a huge difference. For now, we don't really know. For now, the best explanation is that it's the three-body interaction with the central black hole. But in the future, this might change. Anyway, it's still pretty exciting that we've discovered pretty much the fastest main sequence star in the galaxy. And it's possible that this record is not going to be beat anytime soon, because that's basically a really high velocity. Hello wonderful person, this is Anton, and in this video we're going to be talking about a discovery of a really ancient star. Possibly even one of the oldest stars we've discovered so far. But more specifically, I also wanted to talk about how we know the age of these old stars and what makes them so unique compared to other stars in the galaxy. So right now we're in the middle of what's known as a globular cluster. This is a very large collection of usually thousands and then possibly even millions of stars, and many of these stars are really old and were created at the same time. Normally when we look for old stars, we'll look in a globular cluster, but not always. Here is actually a Hubble image of a very well-known globular cluster known as M80, and in here many stars are very old, and they're also relatively similar in age because we believe that in globular clusters usually stars form at the same time. So when it comes to these unusual objects, we can calculate the age of stars relatively easily because they're not very far off from one another. However, if we were to try to determine an age of just a single star out there, specifically if it's completely alone by itself, it would be really challenging. Today we don't really have that many good techniques that can determine the age of a star with a lot of accuracy. Although one of the cooler techniques involves looking at the rotation of the star and then using that to calculate its age. It's actually pretty accurate. But that's usually for stars that are not too old, usually something below 10 billion years old in age. But how do we discover more ancient stars, and how do we know that they're ancient? Well, there's actually a very interesting technique that involves looking at what's inside the star, and if there's nothing but hydrogen and helium in it, we can assume that it's a pretty old star. And so let's just imagine for a second that this right here is a very ancient star. I mean, I don't know if it is, it's actually procedurally generated, but let's imagine that it is. How would we know that it's old? Well, we can look at something known as metallicity. In science, or specifically astronomy, metallicity doesn't mean metals like iron. It just means materials that are not hydrogen or helium. So in other words, in astronomy, scientists often describe hydrogen as letter X, helium as the letter Y, and everything that's not hydrogen or helium, basically hundreds of other elements, just as the letter Z. And Z is referred to as metallicity. Now for our sun, for example, if we were to look at our sun, we would discover the metallicity of roughly around 0.02, which basically means that there's about 2% of metals and 98% of hydrogen and helium. And that's kind of roughly how we usually determine the so-called metallicity. But imagine for a second, we looked at a star far, far away, and we discovered that its metallicity is very, very low. Let's just say maybe about 1/1000th of what the sun has. In that case, we would assume that, well, maybe this star was actually created really long time ago, when basically only hydrogen and helium was around, and it was created from a supernova of early stars. And that is essentially how we discovered some of the most ancient stars in the universe so far, or at least in our galaxy. And here are actually some of them that I created in Universe Sandbox. We have this one here called Kerel star, we have another one called Kafau star, and then a third one known as Snedden's star. They all have names, and that's because they're named after their discoverers. All three of these stars are really, really low in metallicity. But so far the record holder was another star. This star right here, unofficially known as the Methuselah star, named after a biblical character that was supposed to be the oldest human that has ever lived. But the idea here is that this star, more officially known as HD 140283, has one of the lowest metallicities of all of the stars we discovered, and also by measuring some of the other materials in the star, we determined that it must be really old. Practically the age of the universe, or basically a little bit younger. So we think that this is about maybe 13.7 billion years old, just a little bit younger than the universe. And for all four of these stars, the metallicity is pretty low. And if you were to compare the metallicity of these stars to our sun, this one here, for example, has metallicity that's roughly around 250 times lower than our own sun, with some of the other ones actually having even less metallicity. Some of these have 1 divided by 1,000 or even several thousand, suggesting that maybe they're even older. So in that sense, we don't really know which one is the oldest, we just know that all four of these are really ancient. We don't have a technique just yet to discover their precise age. And by the way, we also refer to these stars as population 2 stars. Basically, these are the stars that were produced after all of the initial supernova in the universe that were created by the first stars in existence, that we usually refer to as population 3 stars, then created the so-called population 2 stars, some of which are right here. So all of these stars are definitely really, really old. But then we discovered another star, and this is what we're talking about today. And although it's only been discovered a few months ago, there's only one study so far describing it. But basically this star right here, with a relatively difficult to pronounce name, is now officially the record holder for the lowest metallicity of all of the stars we've discovered. And it's pretty damn low. It's super low. This new star that we just discovered and described in the paper that you can find in the description below is already in its sort of latent stages. It's turned into a very large red giant. But its metallicity compared to our sun is roughly around 1 divided by 1.5 million. Now remember, the oldest star here was only roughly around 1 over 1000. This is like 1,000 times less metallicity than all of these other previous stars. It's kind of difficult to imagine this, but I think one of the astronomers from the paper mentioned that it's sort of like a single drop of water in an entire Olympic pool. And although for our own sun the metallicity is equivalent to about 2% of the entire mass, basically 2% is not hydrogen and helium, for this star it's over 1 million times less. And that suggests to us that this is probably one of the first stars ever created, at least in our galaxy. And so technically this is now the record holder for potentially the oldest star in the galaxy so far. Now at a distance of 35,000 light years away from us, it's going to be relatively challenging to study this. Even though it's already a red giant, it's still pretty hard to see this star. It's just too far away. At the same time, because this star is already a red giant, we believe that it's burning through its helium layers now, and at some point is going to most likely turn into some sort of a white dwarf, similar to what our sun will become. So basically this is the end of this star. It's not really going to stick around for longer than maybe 1 billion years from now, but it's still a very interesting discovery and does create a lot of questions. There is also a very unusual property inside of the star, and one of the things that the scientists are not sure about is why is this star so high in carbon? It's low in everything else, it doesn't have a lot of anything really, there's almost no lithium for example, but it does have high amount of carbon. And to explain this, the scientists think this is kind of what happened. They believe that the first star that existed here, the population 3 star, was not very big. They believe it was only about 10 masses of the sun. It exploded pretty quickly, so it was maybe one of the first supernova in the universe, and this supernova was just not very powerful. And a lot of the material it produced sort of dissipated pretty quickly, and then possibly even fell back into the black hole or the neutron star that was created here, whereas some of the materials like carbon did escape, and all of this material then sort of solidified into the star that the scientists just discovered, and that is what we found. We found a star that was created by this relatively small, not so active, not so explosive supernova in the beginning of the universe. Now we don't really know if this is the oldest star just yet. I'm pretty sure we'll find something even older, but we know that this is the lowest star in metallicity we've ever seen, by a factor of roughly around 1000 at least. In other words, none of the other stars come even close to how low in metallicity this is. Here there's basically just hydrogen and helium, there's almost nothing else. And this creates a very interesting question. Can this possibly have planets around it? This is something that would be really interesting to investigate. If we don't find any planets around this planet, it really suggests that you need to have metals. You need to have things like silicates, things like actual iron to create cores for planets to develop around. If, however, we do discover that this unusual object has some sort of a very large gas giant-like object orbiting around it, well then maybe we were wrong about how planets are created, because we believe today that planets need to have these cores to wrap around, and even objects like Jupiter and Saturn initially had some sort of a solid core that then sort of absorbed all the gas around them. If this here has planets and they're gas giants that were formed, let's just say around carbon, then the creation of planets story needs to be changed, and we need to rethink this whole model once again. And for all we know, maybe these types of planets can actually form objects like Neptune and Uranus, the ice giants, because technically carbon and hydrogen can create methane. So maybe the methane chunks would be enough to create objects like this, and maybe this is what's around this star. In the next few years, I'm sure someone will do a follow-up study and find out what's orbiting the star. For now though, we don't really know, and this particular study in the description below didn't really touch on this in much detail. Nevertheless though, since we've never really seen these so-called original stars, population 3 stars that created all these objects, this is probably our best bet at studying what the early universe material was like, because it seems like everything here, everything inside of this star is practically this primordial material that has never been touched by anything else. Basically, this is a generation 2 star. Whereas objects like our sun right here are more like generation 100 stars. There's so much material that has been reused and reused and reused over and over again that this is technically roughly around 100th generation of stars in existence. And this of course suggests that the universe is just really good at recycling materials and creating new stars. Sometimes even in locations where we never expected stars to be to begin with. Hello wonderful person, this is Anton, and in this video we're going to be talking about a discovery of an unusual star known as hypervelocity star that seems to originate from somewhere in our galaxy where we didn't really expect it to come from. Now what you're seeing right here is a really awesome simulation made from the data collected by the Gaia telescope, and this simulation was created by the European Space Agency to kind of represent what are all of the stars in the vicinity of our planet will actually look like or move to, where they'll move to in the next few millions of years. This is actually a super realistic simulation, and it allows us to not just track the stars and their future location, but also track unusual stars. And because of this data and because of this simulation, ESA was able to discover several really cool stars known as hypervelocity stars. And in this video right here, you're going to actually see some of these stars being tracked by Gaia telescope. And what's interesting is that their velocity suddenly changes dramatically, allowing them to escape our galaxy. And so we've discovered roughly around 30 of these stars so far. And for the most part, some of them are leaving our galaxy. For the most part, some of them are actually coming from the center of our galaxy. And that in itself allows us to explain their origin relatively easy. So here, for example, you can see that some of them are actually coming from other galaxies, but some of them are escaping our own galaxy, coming from the regions of space where we know that they could have been kicked out by, for example, a supernova. If there are two stars and one of them goes supernova, it might get enough velocity to get kicked out. Or they might have gotten kicked out by the central supermassive black hole Sagittarius A star in the middle of the galaxy. But we've just discovered at least one of these unusual stars that seems to be escaping from a completely different region of galaxy where there's really nothing. There's no supernova there. There also seems to be no supermassive black holes, suggesting that something really unusual kicked it out. Now we're going to use this relatively rough simulation in Universe Sandbox with the Milky Way being right here and the star that we discovered right here. So it's approximately, well actually just over 40,000 light years away from our own planet, and it's already quite far away from the Milky Way. And it's moving away from it at a speed of approximately 568 kilometers per second, meaning that it's moving at faster than the speed of stars that are inside the galaxy, approximately double the speed actually. I believe our own sun moves at just half of that, just over 280 kilometers per second. Now this star is known as Lambros HVS1, and it's a very interesting star. Even ignoring the fact that it's moving so fast, it's interesting because it's somewhat sun-like, but a lot more massive. It's, I believe, about 8.3 masses of the sun, which means that it's not going to live as long, but still it's very sun-like, it's relatively young, and also very high in metallicity, higher than the sun. Now, if you don't know what metallicity means, it's essentially things that are not hydrogen, not helium, that are present in this star system. Now, what it usually refers to is how likely is this star going to have planets. Okay, not just planets, terrestrial planets. So terrestrial planets are made from stuff that's metallic, that's not hydrogen, not helium. And because this particular star is higher in metallicity than our sun, there's a very high chance that it might actually have quite a lot of rocky planets orbiting around it that are, well, similar to Earth, similar to Mercury, Mars, and Venus. Now, these rocky planets are currently very hypothetical, but their chance of existing and the fact that this star is very similar to our sun is actually pretty high. So for all we know, this particular star system might have its own little worlds with maybe even life there, and it gets to enjoy this beautiful view of the Milky Way from a distance. Now, what else do we know about this star? So we know it moves really fast, it's very similar to the Sun but more metallic, and to some extent we know where it came from. And essentially we know its origin in terms of the location, but we don't really know what made it go that fast. So we know that it came from a region that's not in the center here. It actually came from one of the arms. And if we try to trace this path and we try to see where it really came from, what we realize is that there seems to be nothing there, but it's also a region that's covered by a lot of dust. So we don't really know exactly what's happening there. And so because of this, scientists started to speculate. So what could have given it this boost? Why is it moving so fast? We expect this to move that fast if there's a supernova or if there's a black hole, very, very massive black hole. And so because of this, there are two main propositions now. First one is that maybe there is actually a globular cluster there, similar to, for example, this right here, M13. So these clusters are all over the place. There's actually a lot of them. They often contain a lot of stars, thousands and millions of stars. And we believe that many of them actually contain the elusive intermediate black holes. So that could have actually been enough to kick the star out. If there is a globular cluster here, and if it has an intermediate black hole inside, it may have provided enough boost to give the star a velocity of 568 kilometers per second. But we don't really know this because we don't see it just yet. At the same time, if it was a smaller cluster, like for example, if it was actually just a few stars there, and they were really massive stars, more massive than 8 masses of the Sun, possibly several dozens or even hundreds of masses of the Sun, and if the star passed relatively close to them, it also may have had enough chance to get this slingshot maneuver and get boosted out of the galaxy. So in other words, if this particular star passed close to, let's just say, this star, it may have received enough velocity to get slingshot out of this globular cluster and then move really fast across the skies out of the galaxy. So that's another potential explanation. If it passed by many very massive stars, approximately 100 or even more masses of the Sun. But once again, because we know that it actually came from this region right here known as the Norma arm, and we don't seem to see anything there, no globular clusters as of yet, and also no any kind of black holes or supernova, we're still kind of in the dark about what really happened there. And so for this reason, this unusual sun-like star known as Lambros HVS1 is definitely one of the most curious objects we've discovered, at least this year in 2019. It's probably going to be one of the most interesting hypervelocity stars in general, simply because we can't explain why it's moving that fast, but also because of the way that it's very similar to the Sun, relatively young, and of course very high in metallicity. We don't expect these stars to have such high metallicity, meaning that this star was produced after a supernova of a very massive star, and also potentially has many terrestrial planets there. So this could be a really cool object to actually take a look at in more detail one day. But unfortunately, since we don't really know much else about these hypervelocity stars, and because we've only discovered like 30 of them as of today, with the first one only being discovered something like 14 years ago in 2005, this by itself is already a pretty cool discovery. So these hypervelocity stars will hopefully one day be a little bit more clear to us. We'll hopefully know a little bit more about them. But for now, all we know is that there's a lot of these stars flying around the universe, coming in and leaving our galaxy at all times, and many of them came from galaxies really far away. And luckily for us, the Gaia mission that's tracking all of this and is making a really detailed map of nearby space will help us find more of these stars and hopefully help us explain their origin and of course the origin of the universe itself. For now though, I think that's all I'm going to say in this video, because there is unfortunately nothing else to add other than it's a cool discovery. Hello wonderful person, this is Anton, and this right here is a magnetar, an extremely powerful neutron star with a ridiculously powerful magnetic field. It would most likely kill you at this distance. And today we'll discuss the study that may have figured out how all of this is created in the universe. In other words, we may have finally solved the mystery of their origin. I wanted to start this video with a little visualization of, okay, this is a moon being destroyed by Earth by tidal effects, not exactly what I wanted to start with. I wanted to put a neutron star next to our planet just to give you an idea at which distance it's very likely pretty much most of us would perish almost instantly. And first of all, at this distance, pretty much all of the technology would cease to exist. Everything would be completely demagnetized and nothing would work anymore. There's that neutron star that's roughly around 1.4 masses of the Sun. Now, if I were to move it to a distance of about 1,000 kilometers away from Earth, although technically we should be moving Earth here because Earth is way less massive. So here comes Earth, it's slowly approaching the neutron star that's right there, right in the middle. You can even see how everything is being sucked into it right now. But at this distance you can see that the tidal effects are so great that they literally destroy our planet. And that's not even the worst part here. The worst part is the actual magnetic effects themselves. The magnetic field of this object is so strong that it would literally... Okay, I just destroyed it by accident. Let's go back to the neutron star. So as I was saying, at this distance, the effects of this neutron star would literally make everything inside your body stop working. The magnetic field here would be so extremely high that every single life process in your body would just stop completely. You would literally just cease to exist. You would die instantly. Now, talk about instant death, right? But there are actually a few things about magnetars that are a little bit different from a typical neutron star. For one, we know that magnetars on average spin way faster, and that's probably why they have so much more magnetic field. A typical magnetar will almost always spin at least once per second or even faster. And this is probably why they have so much magnetic field, because by spinning they do create a lot of magnetic field coming from the inside. At the same time, a very unusual property that magnetars have that other neutron stars don't is that they seem to produce a lot of gamma rays and a lot of X-rays, a lot of really powerful radiation. Some of these scientists suggested that this could potentially be another thing we need to watch out for, because a typical magnetar can produce so much energy that it could hypothetically wipe out life on our planet. But this is going to be a topic for another video that's going to be coming up, where we're going to discuss how occasionally neutron stars, and specifically magnetars, could have caused mass extinction events or may do so in the future. Another really unusual property of magnetars is that for the most part, they don't actually last very long. In other words, after about 10,000 years or so, they become regular neutron stars, which is why there are not that many to begin with in our galaxy, because they simply just become regular neutron stars. However, the total number of these objects in the galaxy could be as high as 30 million. Most of these are already off and no longer produce magnetic energy and basically are literally just neutron stars. Nevertheless, what we need to learn about them is whether they can actually go back up to being magnetars. Can they somehow re-enable? And that could be something dangerous, because a magnetar nearby would definitely cause a lot of problems for humanity. And one of these problems, or actually three of these problems, have been detected in the past. These are so-called gamma ray flares that we believe are produced by magnetars that suddenly have a kind of a starquake on their surface. So by studying these objects, we definitely will learn a lot more about the possible dangers, but also maybe even learn something in the process on how to create energy and how to use very powerful magnetic fields for the benefit of humanity. And there's actually a really important reason for us to study these objects, mostly because the physics near them becomes completely incomprehensible. For example, here the magnetic field is so powerful that it actually turns vacuum itself into a polarized thing. The vacuum is no longer vacuum. It starts acting as something completely different, and even the atoms themselves start stretching so much that they turn into really long objects. For example, various atoms of hydrogen that is still present here would turn into these long needles 200 to maybe 300 times longer than usual. So in a nutshell, the effects here are so dramatic and so extreme that we would want to understand what happens, because we could technically produce very high magnetic fields on Earth, and maybe by producing these fields or something close to these fields here on Earth, we would be able to learn a lot more about science involved and of course about the effects that they produce. But because magnetars are the most powerful magnets in the universe, we're not even close to being able to produce anything as powerful. These objects are just really extreme. And all of this is of course due to the nature of the neutron star, an extremely dense object that is capable of producing effects that we just don't see anywhere else in the universe. But because this is not something we can easily produce in a lab, their mysteries will remain mysterious to us for a very long time. But anyway, so these are the magnetars. These are extremely powerful objects, and for some reason there are just not that many of them out there. And we've always had trouble explaining how they form. Scientists had ideas, but the computers were not powerful enough to test those ideas, until now. And so the study that was just released in Nature magazine, that you can also find in the description below, created the simulation finally showing us what may happen to create these objects. Now this is still a theory, it's not actually proven yet, but it's a very solid theory. What you're looking at is a collision between two really massive stars. And we're talking about several masses of the Sun, and both of them coming together and forming one gigantic star. And they create this very unusual but extremely magnetically powerful star known as a blue straggler. We've seen quite a lot of these blue stragglers out there, and this is one of the ones they've studied. This is Tau Scorpii, and they usually all exhibit very similar patterns. First of all, they tend to exist in globular clusters, like this one right here. This is 47 Tucanae, and you can see that there are a few blue stragglers there as well. We can actually kind of try to come up on one of them. It's called blue hypergiant here, but these are essentially blue stragglers. And for the most part, they all exhibit very similar pattern. With time, they come closer and closer to the center of the actual globular cluster, and eventually they turn into unusual objects. And now we think that these unusual objects are the magnetars. In other words, the study is almost positive that it's these blue stragglers that when they go supernova create magnetars, simply because the original magnetic field of these stars is so extremely high. In other words, the process here is really simple. We can summarize all of this in a few steps. So we have these two really massive stars, very likely O-type or possibly B-type stars. Just to give you an example, here's what our Sun looks like in comparison to these giants. And as they orbit around one another, they eventually collide into a single, very large, very massive, and extremely magnetized object that is essentially the so-called blue straggler. This gigantic and extremely powerful object eventually lives out its life, straggles around, and goes supernova. Which of course creates the leftover behind, and this leftover is the neutron star, but in this case, because it's so extremely magnetic, it's actually a magnetar. And it's extremely powerful, it's very energetic and produces so many different effects that even today we're still kind of struggling explaining all of them. Now magnetars are extremely mysterious even today, mostly because there are just not that many that we've found, but we will eventually be able to explain everything we're observing. But luckily to this paper, we may have finally found their origins, and we may have found at least one solution to one of the mysteries. But because these objects are so rare, we are very unlikely to actually see them made in real time. In other words, even though we've seen other neutron stars being created, the blue stragglers are already very rare. And so for a blue straggler to go supernova and create an actual magnetar in front of our eyes, we will have to get very lucky. It's probably not going to happen in our lifetimes. Nevertheless though, it's a very interesting study, a very cool discovery, and being able to use very powerful computers to find solutions to these kinds of problems is really what makes modern science so beautiful and so wonderful. Hello wonderful person, this is Anton, and in this video we're going to be talking about a galaxy that's relatively close to us, but is never really talked about very often. A galaxy that's not very well known, even though it is quite easily visible. We are also going to talk about a discovery coming from this galaxy that helps us explain how certain stars form. So what you're looking at right here is our representation of the Milky Way galaxy, our own home. Now by now I think pretty much almost everyone is familiar with the Andromeda galaxy, which can be seen right there in the night skies. It is relatively far from us, it's about 2.5 million light years away, but at the same time it's very well known. Now, I'm not entirely sure why the Andromeda became so popular over the years, but it is larger and possibly more massive than the Milky Way, and it's also, of course, on a collision course with our galaxy. But if you look nearby, if you look around, you will discover a galaxy that we're talking about today. It's actually not very far from Andromeda, and specifically it's somewhere right here in this region, and this is the Triangulum Galaxy, a galaxy, as you can see, that's also quite visible, but somehow a lot more obscure and way less known than the Andromeda. This is kind of what the simulated version of this galaxy looks like, but if you were to point your telescope at it, you would see something like this. If you do have a telescope at home and you also have a dark enough skies, you can definitely try to check it out. It's a beautiful galaxy. Here's actually a much more detailed version of this image, and it contains some of the most active regions in the nearby space. It produces a lot of stars, roughly around 5 times faster than the Andromeda galaxy, and it's also a place with a lot of really highly energetic areas. And specifically this region right here that's part of the galaxy is one of the most well-studied and well-known nurseries for basically the creation of new stars. It's very highly energetic, it contains a lot of hydrogen and is quite easily visible. The Triangulum Galaxy is also very peculiar because right at the center of the galaxy, just as you would expect, it has a lot of really highly energetic activity. And specifically right there in the middle of this galaxy is an extremely powerful X-ray source that is actually even more powerful than the one in the middle of Andromeda Galaxy. But what is really unusual about this galaxy is that even though you would think it's some sort of a black hole, it seems that this galaxy does not contain any supermassive black hole at its center. And the unusual X-ray source is caused by something else, something extremely mysterious. Some scientists suggested that the black hole might be there, just a lot smaller, possibly less than 3,000 masses of our sun, but if that is so, it still doesn't explain what causes this particular X-ray source. So there's at least one mystery we still don't really know how to solve. And by the way, this right here, also known as NGC 604, is also simulated in Space Engine, and you can kind of see it right there. It's a very easily visible nebula-like formation. So this right here is where a lot of new stars are formed, and it's an extremely beautiful and exceptionally bright area of this galaxy. Apart from that, there are actually quite a lot of other really interesting and really unusual discoveries related to this galaxy, which we'll probably cover in some of the future videos, but I think the one I wanted to mention here is in regards to the biggest stellar mass black hole we've discovered. Basically, a typical black hole that orbits around another object is also in this galaxy, and you can easily find this in Space Engine by looking up an object known as M33 X-7. So there's a black hole right here, it's about 15 or over 15 masses of the sun, and it's the largest stellar mass black hole we've ever discovered. Basically a typical black hole that orbits around another object and produces a lot of radiation. But none of this still explains to me personally why this galaxy is just not really popular. It's not really talked about that much. I guess it is a little bit smaller than the Milky Way. It's roughly around 60% the size of our galaxy, and it has about 10 times less stars in general, but it's a very exciting place, and which is why this study that's coming out of Japan is kind of exciting to cover, because we finally are talking about the Triangulum Galaxy. So what exactly did the Japanese scientists discover? Well, these scientists were studying the creation of really massive stars. Specifically stars that are so massive that they usually live only a few million years and then explode, producing extremely large and very bright supernova. And actually a star that orbits the black hole I just showed you is one such example. We are not entirely sure how they're formed. There are some speculations that maybe they're formed when several stars combine together, or maybe they somehow form through interactions of various clouds in the galaxy. And so these Japanese scientists were able to not just discover but visually show us how these stars are formed, and all of this is done by looking at the Triangulum Galaxy where many stars are formed right now. What they did was zoom into one part of the galaxy right here, where they found these really large clouds of gas, and this gas is slowly coming together. And basically imagine that there are several really large dust clouds, something like 200 light years across, possibly containing over 50,000 masses of the Sun in total, all of them kind of slowly colliding into another and creating these large formations. And so they looked at these clouds using various frequencies in various telescopes to make sure that they're not just looking at the visual perspective, but also at the radio frequencies that would be produced by, for example, hydrogen or carbon monoxide or other molecules that are in this area. And after this, they used the data from the Hubble telescope to look at the same area to see what's really there. And what they discovered are these really large bright spots indicating that there are supermassive, extremely large and extremely bright stars that were just formed not so long ago, possibly within about 500,000 years from when we're observing them. And they've basically discovered roughly around 10 stars, all in the same region. All of these are very bright O or B stars, pretty much similar to what you see right here, an extremely powerful, extremely large star that is going to live only a few million years and then explode in a supernova, producing more radiation, more clouds, and materials that might one day form a sun-like star. And so this study definitely showed us visually, and kind of proves once and for all, that these large and massive stars that eventually result in stars like our Sun are formed by the collision of these clouds, many of which are happening right now and will be happening for many years to come in the Triangulum Galaxy. So this is definitely a place for us to study star formation. Now, it's still not entirely clear what even caused these clouds to form and what possibly led to their collision, but we know that this will probably happen again, specifically in a few billion years from now, when this galaxy has a very high chance of colliding with the Milky Way. As a matter of fact, today there's a lot of evidence to suggest that the Triangulum Galaxy, also known as M33, will very likely come in front of the Andromeda and collide with the Milky Way first before the Andromeda Galaxy joins and forms a very large, extremely massive galaxy, possibly known as Milkdromeda. We don't really have a good name for it yet. But the idea of the collision between Triangulum and the Milky Way is still being explored because we're not entirely sure of what the actual speed of both of these galaxies in relation to the Milky Way is yet. We just know that they're headed our way, we're just not sure who is going to come here first. And if the galactic collision with the Triangulum Galaxy does happen first, it's very likely it's going to happen in about 2.5 billion years from today. So by the time when, well, our Earth is probably not going to be habitable anymore, and it's very likely that the Sun is still going to be just as bright and as powerful as it is today, possibly even hotter. But it's not going to be a red giant yet. And following this collision, it's very likely that the shape of the Milky Way will change quite a lot, and it's also very likely that once the Andromeda joins in, our galaxy will become something similar to many different elliptical galaxies, like for example M87. It might not have a very regular shape, it might be very different from what we even imagine today, but it's probably not going to be a typical spiral galaxy for quite a long time, until gravity stabilizes its shape. But anyway, we'll talk more about galactic collisions in some of the future videos. For now, I really just wanted to talk about the Triangulum Galaxy. I've only made one video about this galaxy over the existence of this channel, and it's a little bit embarrassing that we don't talk more about it. There are actually not enough papers on this galaxy, even though there are a lot of really cool things happening here. Hello wonderful person, this is Anton, and in this video we're going to be talking about these unusual objects known as spider pulsars. These are very unusual neutron stars that tend to destroy their partners. So before we start talking about what spider pulsars are, let's take a look at this. This is actually one of the most well-known pulsars, Crab pulsar. This is in the middle of Crab Nebula, and this is actually in real time. These tremendously powerful objects spin ridiculously fast, and in the middle there, the actual radius of this object is roughly around 10 kilometers. So basically what you're looking at is this 20-kilometer large ball of matter that's spinning super fast and is producing all of this energy around it. Now, sometimes we get to see these objects when they emit these astrophysical jets, but sometimes we get to see them for other reasons. And this is kind of the case with the so-called spider pulsars. Now, a spider pulsar is actually two types of different pulsars. They're either black widow pulsars or redback pulsars. Now, what exactly is the difference? Well, actually, it has all to do with the partner. So this object right here, known as B1957+20, is actually the first ever Black Widow pulsar discovered. It's basically a neutron star, a very massive neutron star, probably one of the most massive we've ever discovered. But as you can see, it has no actual astrophysical jet and possibly not even an accretion disk. But it has something else instead. It has a partner. And in this case, this is actually a brown dwarf. Now, this brown dwarf is really close to the parent star. And as a matter of fact, it's so close to it that the actual interactions, like for example, tidal interactions and radiation interactions between the neutron star and this object make it sort of shrink. It makes it lose all of its matter, all of its atmosphere, and it constantly loses everything basically. It sort of evaporates non-stop. And when this object is relatively small, like for example less than 10% the mass of the sun, we refer to them as black widows. I guess because they are very good at destroying their partners. Whereas if it's anything bigger than that, but still smaller than a star, we refer to them as redbacks. That's also another type of a spider, by the way. So we've actually taken a photo of this particular pulsar, and what we saw was something like this. Now this is a photo, but it's a little bit difficult to understand what's happening. But there is an even better recreation created by the scientists that shows you that essentially right here in the middle is the neutron star, and it's sort of flying through this halo of material that was released by its partner, and all of this is generating some types of energy that we can then detect from Earth. So that's kind of what you're seeing here. But if you were to zoom in to the star itself, what you would see would be this. A very unfortunate interaction between the neutron star in the middle and the brown dwarf that's basically literally being stripped of everything. And this tail that's formed by this brown dwarf is then formed into a halo. So these types of objects are actually quite common. We've found quite a lot of them, but very recently we've discovered another one that has actually been very thoroughly studied in the very recent paper, which you can of course find in the description below. So this particular pulsar, known as J09520607, is also the second ever fastest pulsar. What this means is that particular pulsar is spinning 707 times per second. And that is ridiculously fast. It's actually almost at the limit of the highest speed possible before neutron stars fall apart. Now we think that it acquired this speed by eating up a lot of the mass from its neighbor, and the neighbor here is once again a relatively small, possibly about 2% the mass of the sun object that's very likely a brown dwarf. Now this brown dwarf is not really providing any mass to its partner that you can see in the background right there, but it is, however, losing a lot of mass, and as a matter of fact basically is being stripped of a lot of material through various interactions with its partner. And because of this, it once again qualifies as a kind of a Black Widow pulsar. Now there's a lot of other things that these scientists in this paper discovered about this system, like for example that it takes this object approximately 6.4 hours to go around the pulsar, and that the pulsar itself is actually kind of slowing down just a little bit, but it will take it a long time before it finally slows down. Because basically for every second here, it only loses about 1 trillionth of a second of rotation. In other words, it's going to take a long while before it slows down. But one of the more major discoveries was that apparently this object is one of the least magnetized neutron stars we've detected. Usually neutron stars are actually quite magnetic, but this one doesn't seem to be that magnetic, and they were not really able to explain why. The magnetism here is still pretty high, but compared to other neutron stars, it's basically in bottom 10. And this suggests that maybe these Black Widow stars, or I guess redback stars, are not actually that magnetic because they don't really get much material from their partners anymore. They destroy the partners, but they don't really absorb it, and they don't really create very large magnetic fields. And lastly, this is actually one of the few active pulsars that we were able to detect outside of an actual globular cluster. In most cases, all of or most of the neutron stars were actually discovered in one of the major globular clusters, like for example this one right here. This one is known as Tarzan 5, and that's the globular cluster that we studied quite extensively and have discovered something like a third of all pulsars deep inside of this. Usually it's a lot easier to find pulsars in these, and they're more likely to be created here as well. But discovering one outside of a globular cluster is also very unusual, and on top of that, such a fast-moving pulsar with such a high spin. So in that sense, the newly discovered pulsar is actually kind of an anomaly. It's not really well understood, it's not really something that we're going to be able to explain anytime soon, and because it's probably going to take us a while to find another similar pulsar, this is probably going to be one of those really rare, unique ones. So some of the future studies might establish how exactly it was formed and how it was able to get such a high speed of spin. For now though, that's kind of all we know about it. It's a very unusual type of a pulsar. It's destroying its partner without really eating much of its actual mass, and it's creating these unusual bow shocks that are visible from a really far away distance. Once we discover more about this unusual pulsar, or better even, once we find more unusual neutron stars, unusual magnetars, or really cool pulsars, I'm definitely going to come back and make another video about these. But for now, that's really it. Thank you so much for watching. Hopefully you know a little bit more about space and universe from this video. And if you've enjoyed this, don't forget to subscribe, share this video with someone who enjoys learning about space and sciences, come back tomorrow to learn something else. And maybe even consider supporting this channel on Patreon, because it does help me quite a lot. I'll see you tomorrow. Space out, and as always, bye bye.